All right. So the next batch of examples are mostly about some function given to you. And the question is, what is the Taylor series of this function, say, centered at 0? So obviously, you can go back to the definition, find the coefficients of the Taylor series of the given function by differentiating that function, finding higher derivatives, evaluating the higher derivatives at the center. So the nth derivative would be the nth coefficient would be the nth derivative of f evaluated at the center divided by n factorial. Those are the coefficients of the Taylor series, and then produce the Taylor series. However, almost exclusively in all of these problems, the given function may not be one of these famous functions that we talked about. They may not be e to the x or sine x or cosine x or 1 over 1 plus x, etc. But they can be related to these. Somehow there may be some distant cousin of one of these functions. And in such cases, there is a shortcut. You don't have to go back and produce the Taylor series from the scratch by computing all the coefficients one by one. That would be a bad idea. It would be correct, but not the most efficient way. The shortcut is you somehow relate the given function to one of these familiar functions, use your knowledge of the power series of these familiar functions to simply produce the power series of the given function. So let me explain this idea in this first example. Taylor series of e to the 3x squared at 0. In other words, I want to find the Maclaurin series of e to the 3x squared. Method number 1, the wrong method. Mathematically correct, but it's a bad choice. Sit down and keep taking derivative of this function. Find the nth derivative, evaluate it at 0, and then divided by n factorial. That would be the nth coefficient, and then produce your Taylor series. That is mathematically correct, but very tedious. Much better method. Use the fact that this guy is some form of an exponential function. It's just e to the x in which I have replaced x with 3x squared. So why not taking the Taylor series of e to the x, and everywhere, instead of x, I plug in 3x squared. So that will be a much more efficient method. So use Taylor series of e to the x and replace x with 3x squared. If you replace x with 3x squared in e to the x, you get e to the 3x squared. On the other hand, if you replace x with 3x squared in the Taylor series of e to the x, you get the Taylor series of 3x. So that will give you this formula, e to the 3x squared. So in my mind, I remember what the Taylor series of e to the x was. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So it's going to be 1 plus 3x squared plus 3x squared over 2 factorial plus 3x squared cubed over 3 factorial plus 3x squared to the 4th over 4 factorial, and so on. And now if you want, you can simplify this a little bit. If you want to get, if you want to get the first few terms, 1 plus 3x squared plus 9 over 2 x to the fourth, because here I have 3 squared, which is 9 divided by this, and then 3 cubed, 3 cubed, which is 27, divided by 6, which is 9 over 2 again, right? Yeah. 9 over 2 x to the 6 plus whatever, 81 over 24, which is 27 over 8. I can so those are the first few terms in the Taylor series of e to the 3x squared. If you wanted to, so a lot of times in order to estimate something, it's better if you just see directly the first few terms. But if you wanted to write the Taylor series in closed form using the sigma notation, you could also do that. You could say that, remember, the e to the x power series in sigma notation is this guy, x to the n over n factorial, right? And now, if in this power series I replace x by 3x squared, I get this power series. So that would be the closed form. So let me just say that in closed form. By closed form, I mean a compact formula that's not like listing the first terms and then saying dot, dot, dot. When you write it using the sigma notation, you are actually making a more precise statement very compactly. So this is going to be 3x squared to the power n divided by n factorial, which I can also write as you want. You can also write this as 3 to the n, and then x to the power 2n. So that would be another way of writing this power series in closed form. Now, if you keep substituting various successive values for n, starting at n equals 0, you get this term. For n equals 1, you get this term. For n equals 2, you get this term, and so on. Is this clear? Are you happy with this, or there is a question before I move on to the next example? Good. Similar idea here. It would be very difficult to compute the Taylor series of this function, x cosine 2x, from the scratch, namely by finding f prime, f double prime, f triple prime, the nth derivative of f, and then evaluating them at the origin in order to find the nth coefficient. Because look at this. Every time you have to apply the product rule, and it gets more and more complex. So what is the remedy? The remedy is I see cosine here, and I think of this function as maybe some distant cousin of cosine. Somehow, if I know something about cosine, I should be able to say something about this function, and that's in fact true. I take the already known Taylor series of cosine x, I replace x with 2x everywhere in that power series. That will give me the power series of cosine 2x. And then I multiply that power series through by an extra x. And that should give me the power series of Taylor series of this function. So I can just say that x cosine 2x is x times. So let me, maybe for the record, let me just mention this here, that we use Taylor series of cosine x and replace x with 2x. So Taylor series of cosine x starts like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial and so on. So this is going to be 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial, etc., etc., which I can write as x. So I'm going to take this x and I'm going to distribute it inside. So that's going to be x minus, this guy is 4 x squared divided by 2, so it's 2x squared, so it's going to be 2x cubed plus, this is going to be 2 to the 4th is 16. On the bottom, I have 24. So it's 2/3 plus 2/3 of x to the 5th times x to the 5th minus, I'm sorry, this is 6 factorial, minus whatever. 2 to the 6th is what, 128? 64. 2 to the 6th is 64, and 6 factorial. So 64 divided by 6 times 5 times 4 times 2 times 3. So 8. And that's it. So it's 8 over 90, right? Which is 4 over 45. So this is 4 over 45 x to the power 7 plus etc., etc. So those are the first few terms in my power series. Double check this. I did it very quickly, but whatever it is, 2 to the 6 divided by 6 factorial. I think that's correct, but we have to double check this. What about the closed form? In closed form, if I wanted to write it in closed form, I would take the, so let's start with the Taylor series of cosine x and then tweak it. Taylor series of cosine x is minus 1 to the n over 2n plus 1 factorial times x to the 2n plus times x to the 2n. Sorry, 2n factorial on the bottom, not 2n plus 1. We're talking about cosine. 2n factorial times x to the 2n. That's cosine, right? And then cosine 2x means I have to replace my x by 2x. So here I get 2x to the power 2n, which is 2 to the power 2n times x to the power 2n. So this is, so far, this is cosine of 2x. And then I have to multiply it by x, because my function is x times cosine 2x. So when I do that, it's like raising every power by 1. So x to the 2n becomes x to the 2n plus 1. So if you want to write it in closed form, that's it. Let me just write it neat and clean. But I showed you how I would do it on my scrap paper, so you can see how this thing develops in real time. It's not like I know it ahead of time. I just like you, I have to grab a piece of paper and compute this thing. So this is it in closed form. But the whole thing is kind of elementary. You start with the formula for cosine, you replace x by 2x, and then you multiply it by x. Are you happy with this? Is there any question? Is there anything about this example that you're not happy with? And maybe in the back of your mind, you think that, okay, something is fishy. I'm not following. Okay. All right. I'll take that as a yes. Now, this example is very nice, and that um, in the end we get a result that's often known as the binomial formula, and this goes back to Newton himself. So Newton was the first person who actually developed this general version of the binomial formula. So everybody knows that 1 plus x squared is 1 plus 2x plus x squared, right? And 1 plus x cubed is 1 plus 3x plus 3x squared plus x cubed. And similarly, you can find 1 plus x to any power, say 10, and these coefficients can be computed. These are actually the so-called binomial coefficients that come up in combinatorics. They have combinatorial descriptions. So this is a well-known idea. Here, we want to expand 1 plus x to the power k into a power series, but our k is not necessarily an integer. It's not a whole number. It's not 1, 2, 3, 4. It could be anything. So for example, k could be a fraction, 2/3, 1/2. It could be an irrational number. It could be pi, like 1 plus x to the power pi. It could be sort of arbitrary. So what we are trying to do here is slightly more general than the elementary case of 1 plus x squared or 1 plus x cubed and so on. So I'm going to show you the first few terms of the Taylor series of this function centered at 0, and then you'll see the pattern. So what do I need? I need f of 0, which is just 1 to the power k, which is 1. F prime of x, I need to take the derivative and then evaluate it at 0. So f prime of x is k times 1 plus x to the power k minus 1. So f prime of 0, if you evaluate this derivative at 0, you get k. Let's take one more derivative, f double prime, the second derivative is k times k minus 1, 1 plus x to the power k minus 2. So the second derivative at the origin would be k times k minus 1. And now you more or less see the pattern. A clear pattern is emerging. Let's do one more. The third derivative, remember, k is a fixed number. X is your variable, k is a fixed number. So think of like 5, something fixed. So it's going to be k times k minus 1 times k minus 2, 1 plus x to the power k minus 3, which means the third derivative at the origin is k times k minus 1. If you plug in 0 for x, this term will be 1. So you just get this. K times k minus 1 times k minus 2. So look at the pattern. The first one is 1, then k, k times k minus 1, k times k minus 1 times k minus 2. The next one will be k times k minus 1 times k minus 2 times k minus 3. It's obvious that what the pattern is. And therefore, the Taylor series so I'm not going to prove this, but this is in fact true that the function is equal to its Taylor series. So 1 plus x to the power k, you can write it as its Taylor series. So it starts with the constant term 1 plus f prime of 0 times x, so it's kx, plus f double prime at 0 over 2 factorial times x squared, so it's k times k minus 1 over 2 factorial times x squared, plus the third derivative at the origin, which is k times k minus 1 times k minus 2 divided by 3 factorial, namely 6 times x cubed, and so on. So what would be the next term, for example, when I put ellipses and say that, and so on? Well, you see the pattern. The next term will be k times k minus 1 times k minus 2 times k minus 3 divided by 4 factorial. That would be the coefficient times x to the 4th. And so on. So this is a very nice result called the binomial formula due to Newton. This is called the binomial formula. And in this binomial formula, one can show that this formula is correct if x is between -1 and 1. So the radius of convergence of this power series on the right is 1. The interval of convergence is -1 to 1. And this power series, as a matter of fact, is equal to the function 1 plus x to the power k. One special case of this formula we have seen before. Can you tell me which special case? For some special value of k, this formula is something we've seen before. What is that? If you go back to the list of the well-known formulas that obviously it can't be any of these because these were exponential and sine and cosine. Which of these guys is a special case of the binomial theorem? Very good. You see, if k is -1, Ying, you're absolutely right. If k is -1 in this formula, what am I talking about? I'm talking about 1 plus x to the power -1. In other words, I'm talking about 1 over 1 plus x. So that case we've seen before. And you see, if k is -1, you get 1 minus x plus x squared, because this becomes plus 1. If k is -1, you get -1 times -2. So the top will be 2 divided by 2. You get 1. So it will read 1 minus x plus x squared. And you can see that this will be -1. So minus x cubed and so on. So these coefficients will be +1 -1 +1 -1 in an alternating fashion. And this is the good old expansion for 1 over 1 plus x that we derived using the formula for the geometric series. So I just wanted to mention that this is something, that special case, that very special case is something we've seen before. But obviously, this is much more general because it applies to many other. So let me just mention in passing that the case is the formula for 1 over 1 plus x that we have seen before. Okay. So this is not really difficult to keep in mind or memorize because, again, this is something very useful. 1 plus x to the k. A lot of people who actually use this type of approximation on a daily basis in their work, they usually use the linear part. So if x is very small, if x is a small quantity near the origin, which is the center of this approximation, 1 plus x to the power k would be roughly 1 plus kx. That's the meaning of it. For example, they would say, if they want to know square root of 1.08, this is 1.08 to the power 1/2, right? So this is roughly 1 plus half of that thing, which is 0.04. So it's roughly 1.04. And that's the good approximation that you can quickly come up with without the intervention of a calculator. So that would be a typical quick type of estimate that you can make using this formula. In general, for example, square root of 1 plus a small quantity x is roughly 1 plus half of x, which is this part of this approximation. So if I just ignore this part and say that for small x, this part is negligible. So for small x, 1 plus x to the power 1/2 is approximately 1 plus 1/2 x. Why not equal? Because I'm ignoring the rest of the terms. So that will not, I'm going to lose something in terms of accuracy. But if x is very small, this is a very good approximation. You want a better approximation? Incorporate the next term also. So take the first 3 terms instead of the first 2 terms. Make it quadratic. You want a better approximation? make it cubic. That's the idea. The more terms you add, the better the approximation will be. But the thing is, if x is very close to the origin, chances are only the linear term would do a good job. Okay? These are the type of back of the envelope estimations that people use all the time. Let's take a look at this example. That's an ugly 2. You write it again. So find the second Taylor polynomial t sub 2 for this function. F of x is 1 over square root of 5 minus x at the origin. You have two options. Option number 1, start from the scratch. Starting from the scratch means, what is the Taylor polynomial, the second Taylor polynomial t2 of a function? Center is 0, so it would be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared. That's t2. So if you want to do this from the scratch, it means you need this coefficient, f of 0, you need this coefficient, f prime of 0, and you need this coefficient, f double prime of 0 over 2. Not a big deal. Sit down, take this function, take the derivative, evaluate it at 0. And then take one more derivative, evaluate it at 0 to see what you get. You know what? I think we have time because we have like 10 minutes. So let me just show you this. This is a good exercise. I wanted to just tell you that it could be done this way. So let me do it in 2 different ways quickly. This whole thing won't take more than definitely less than 10 minutes. So I'm going to do it from, I'm going to evaluate T2 from the scratch, and then I'm going to show you how you could find this quickly using your knowledge of the binomial theorem in the previous slide. Okay, so that's the plan. So direct method. So for direct method, I know that T2 is f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 times x squared. 2 factorial is 2, so I don't write it as 2 factorial. So I need these guys. I need this number, and I need this number. All right, so f of 0, what is f of 0? That's the formula for f. So f of 0 is just 1 over root 5. And by the way, I can write my f of x because I'm going to take the derivative, so it's easier if I write my f of x as 5 minus x to the power minus 1/2, because then differentiation becomes easier. So yeah, if I want to write everything neat and clean, I can put this over here, and then I can write the derivatives underneath. I can say that this implies that f of 0 is 5 to the power minus 1/2, which is the same as 1 over root 5 that I had before, but doesn't matter. F prime is minus 1/2, 5 minus x to the power minus 1/2 minus 1 minus 3/2 times the derivative of 5 minus x, which is minus 1, chain rule, so this becomes plus. So I have not forgotten that negative here. There was a negative, but by the chain rule, I have to multiply by the derivative of 5 minus x, so minus minus is plus, so that's not a typo. And that means f prime evaluated at the origin is 1/2 5 to the power negative 3/2. And one more time, I also need the second derivative at the origin. So let's take one more derivative. Minus 3/4. 5 minus x to the power minus 5/2 times -1. So this minus minus is plus. So this is what you get. And therefore, the second derivative at the origin will be 3/4 of 5 to the power minus 5/2. And therefore, instead of these guys, I can put their values. So the first one is 5 to the power this, and then the next one is this. And then the next one is 1/2 of the second derivative, so this should become 3/8. So that is the second Taylor polynomial of that function. Okay? Instead of copying this thing, I simply moved it, so I need a copy of this here. But remember, it was 3/4. How did 3/4 become 3/8 in my formula? Because the coefficient is second derivative at the origin divided by 2 factorial. That's why the 3/4 became 3/8. But anyway, this is how you compute it directly. It's not too complicated because it was simply the second Taylor polynomial. But if somebody asks you to produce the, I don't know, the fifth Taylor polynomial, then it would become more work. But now, instead of this direct method, let me show you the similar computation using the binomial theorem. Using the binomial formula. And this is much quicker because we already have done the hard work. So f of x. So this is going to be my last word. We still have 6 minutes left, but it shouldn't take that long. So this is 5 minus x to the power minus 1/2, right? The binomial formula lets me expand 1 plus x to some power k. This is not 1 plus x. It's 5 minus x. Well, that minus is not important. That's like replacing x by minus x. The thing that's bothering me is this 5. So what was the trick? You need a 1 here, but you have a 5. So the trick is the usual trick. Factor your 5. So factor out your 5. So this is going to be 5 to the power minus 1/2. 1 minus x over 5 to the power minus 1/2. Do you see that? So here, I have factored 5. If you take the 5 out, what's left is 1 minus x over 5. And then 5 to the power minus 1/2 will come out. And now this is ready for the binomial theorem. This is like 1 plus this guy. So it's like 1 plus this guy to the power -1/2. So my k, so you have to replace your x by minus x over 5. And you have to replace your k by -1/2. So what do you get? I have 5 to the -1/2 from before. And now I'm going to expand this guy. It was 1 plus kx. You see, it starts like 1 plus kx plus k times k minus 1 over 2x squared. So this is going to be 1 plus kx, which is -1/2 minus x over 5 plus k times k minus 1 divided by 2 factorial, which is just 2, times x squared, which is minus x over 5 squared. And then I'm not going to bother with the cubic term or x to the 4th term, because my goal is to write the second Taylor polynomial, which means I have to stop at the quadratic term. So that's T2. That's T2 because I stopped at the quadratic term. Now let's clean up. That's 5 to the -1/2. 1 plus 1/10 times x plus, what is this? That's 3/4, 3/8. And I have a 25 here on the bottom. 8 times 25 is 200. X squared. So if you want, you can write this as 1 over root 5 plus 1 over 10 times root 5 x plus 3 over 200 times root 5 x squared. And that's your T2. Now, this guy is the same as this guy. They're just written in 2 different forms. This is in fractional powers of 5. But if you replace for these fractional powers of 5, you see that it's the same as this guy, which looks more familiar in terms of root 5. So we had 2 options. Start the thing, write the thing from the scratch, and using the binomial formula. At this level, you may think that, okay, they're more or less the same amount of work, but if you had to compute more terms, then definitely the binomial formula, which has a clear pattern, would be much easier. Okay? Are there any questions? All right. Okay, folks. So the last lecture. So next week we have a lecture on Tuesday in which I will go over some applications, further applications of Taylor series, and then on Thursday we'll have a review. I'll try to post a review sheet on Google Classroom by the end of the weekend, before Monday, with some practice problems. So we'll go from there. All right. So when is the final? Oh, whatever is on CUNY first. I think it's after the 20th. Does anyone know? It it says on CUNY first, but I forgot. I can double check and post it on the course webpage. But you should assume that that date is accurate. Okay. I don't think they're going to change it. All right. So have a great weekend. Take care and stay safe. You too.